Yeah, thank you. So this is joint work with Thorsten Altenkirch in Nottingham. Let's see, okay. Yeah, so when I mean type theory, I mean Martin-Löf type theory with dependent types here. So our goal is to represent the syntax of type theory inside type theory. So why would we like to do this? One reason is that it's nice to study the meta theory of type theory in a nice language, in the nice language of type theory. And the other is to do template type theory. So just as there is template C++ and template Haskell, and then it makes it very convenient to do metaprogramming, we would like to have the same features for type theory. We would like to express the judgments of type theory with an inductive type. So the main judgment with the inductive type. So the main judgment of type theory is that the term T has type A in context gamma, and we formalize this as having an element of an inductive type, which is term gamma A. So we have typed terms. We don't care about untyped terms. All the elements of this inductive type will be well-typed terms. So as an example, or to give an idea of how to do this for type theory, first I show the case of simple type theory, where we don't have type dependencies, in the notation of Agda. So we define 4 inductive types, this tie, which represents types, con, which represents context, and variables, and then term for terms. And we only have 2 kinds of types. So we have a base type, which is just an element of this inductive set type. And then we have arrow types, which given 2 types, we get a new type. So basically, this inductive type is binary trees with no information at the leaves. And then we define context, which are SNOC lists of types. So there is the empty context. This is the constructor for the empty context. And then we have a constructor which takes a context and extends it with a type and then gives a new context. And then we have variables. But variables are not simply an inductive type, or this set is the notation of Agda for type, but they are a family of types indexed over contexts and types. So for each context and type, we have an inductive type of variables. And these will be type de Bruijn indices. So the 0 de Bruijn index will represent projecting out the last element of the context. And then we have a successor, which given a variable, which from a context gamma gives us a type A. Then we can extend the context by a B and get a variable in the get the same variable of type A in an extended context. And then we have the type of well-typed terms. So we just embed variables. So if I have a variable of type A in context gamma, then I also get a term of type A in context gamma. And then I have applications, which is the usual application rule. So if I have an A arrow B, a term which is a function, which has a function type, and then I have a term which has the domain type, then I get a term of the codomain type. And then I have lambda, which, with the help of which I can abstract over the last element of the context and get a function from with the domain of that last element of the context. So this is one part of how to do simple type theory. But simple type theory, and as well as type theory, includes a conversion relation. So we need extra machinery to represent this inside our theory. So we need to define substitutions or context morphisms from one context to another context, and then applying substitutions to terms. So if I have a term in context gamma, and then I have a way to interpret everything in context gamma by context delta, then I get the substituted term in a context delta. I don't show the definitions of these. And with the help of this, help of substitution, I can define a conversion relation, this tilde relation between terms and between type terms, which includes, for example, the application rule, the beta rule for function space. So if I apply a lambda abstraction, a U to a lambda abstraction, it's the same as the body of the lambda abstraction substituted by a substitution where the last element is the U, what I applied. And then my intended syntax is the quotient of terms by this relation. So how does this change? If we would like to represent the syntax of dependent type theory. So just as before, contexts are built up out of types, but now types also depend on context. So there is a cyclic dependency. And also, substitutions are mentioned in the application rule. So the up constructor for function space needs to mention substitutions. So by this, we are forced to include substitution as well in our data type. And everything will be mutual. So many things, these cyclic dependencies show up everywhere. And this is why we need an inductive definition, which makes it possible. So we will first declare 4 types: context, types, substitutions, and then terms. And even the declaration of the types depend on the previous ones. And then we list all the constructors for all these 4 types. And these inductive definitions allow these cyclic dependencies. But in addition, there is another complication, which makes things much more complicated, is the coercion rule for terms. So if the types A and B are convertible, and then I have a term T in context of type A, then I also get a term in a term of type B. So one of the constructors for terms, which makes this rule, which formalizes this rule, will need to refer to the conversion rule for the conversion relation for terms. So this forces us to define the conversion relations mutually with the whole syntax. So instead of 4 types, now I have 8 inductive, mutually defined types. And this results in a big mess and lots of boilerplate. So there are most of the rules in these rules for these conversion relations are follow some pattern. So they seem like so they are really just boilerplate. We know what to do, and it seems that this situation calls for some abstraction, where I could abstract over all these rules. So there are all the rules for each conversion relation, which says that they are reflexive, symmetric, and transitive. There are all the coercion rules. Then for every constructor that I have, I need to add congruence rules, that they respect all of these relations. So basically, what I end up with is I'm working with setoids and then families of setoids indexed over setoids, and it's a horrible mess we try to do with this. And the feeling is that when you work in this formalization, you just don't see the forest from the trees. It's yeah.
What is a setoid?
A setoid is a type together with a relation, which is an equivalence relation, and then I treat the type, treat that relation as if it was the equality for that type. And then all the constructors need to respect this equality then. And then a mapping between 2 setoids needs to respect these relations as well, and so on. Yeah, so by looking at these three kind of rules which show up a lot of times, we see that there's the identity type in type theory, also called equality, which I write it with this triple equals. So the equality is an equivalence relation. Also, it is possible to coerce between equal types. And it's also a congruence. Everything in type theory respects the identity type. So the question is, could we use these properties of equality to help us in this struggle? But the problem is that it's not only these kind of equalities or these kind of properties that we need to add to the relations, but there are also the rules which we really care about, like beta and eta rule for pi, which we would like to add. And then in this struggling, homotopy type theory comes and helps us by providing higher inductive types, which are inductive types where you can also have constructors for equalities. So an example is this I interval type, which has two usual constructors, 0 and 1, and then another constructor which constructs an equality between 0 and 1, which is called segment. And we can, just as inductive types can be used or made use by eliminators, or an implementation of eliminators might be pattern matching, higher inductive types also come with an eliminator or a recursor. And the recursor for this type looks similar to the one without the segment constructor, but we also have an extra argument of the recursor corresponding to the segment constructor. So we have a motif into which we would like to eliminate, and then an element of the motif for each constructor. And the method for the segment constructor says that these two methods respect this equality. And if I have all of these, if I provide all of these methods, then I will be able to, from an I can go to, from an element of the interval, I can eliminate into this set that I gave to the recursor. And quotient inductive types that we use in our formalization are a special case of higher inductive types. They are truncated to be an H set in the language of homotopy type theory, which means that all the higher equalities are trivial. So equalities between equalities are all trivial. There are no two different equalities. And they are not the same as quotient types. So the quotient type that we might have used for doing simple type theory wouldn't suffice here, because here we really need to define equality at the same time as the other constructors, the equality constructors at the same time as the other constructors. So it's not that first we define the theory and then we quotient by equality, but these are all mutual. And there's a way to simulate them in Agda. And using these techniques, we define the syntax of a basic type theory as a quotient inductive type. So it's not only a quotient inductive type, but because of the 4 different types, it's an inductive type. And in our formalization, we have pi and an uninterpreted family of types U and EL. And in this formalization, we don't need to state the equivalence relation, coercion, and congruence rules anymore. So it's a much more convenient formalization to work with. And just as I showed you the eliminator or the recursor for the interval type, we have a recursor for our syntax, and the arguments of which, if we collect into a big record, like the things that the context needs to map to, the things that the types will be mapped to, and so on, this big record can be viewed as this is the algebra of our inductive type, but it can also be viewed as a model of type theory. So the elements of this record will be models of type theory, and this record is a formulation of categories with families, which are a well-known notion of what a model of type theory is. But they come out, so all the types in the record come out automatically from the definition of the inductive type. And we use this formalization to build some models. So as a sanity check, we built the standard model or the metacircular model, where every object theory construct is interpreted by the corresponding thing in meta theory. So contexts are interpreted as sets. Types over the interpretation of contexts are interpreted as families over that set. Object theory, function space, dependent function space is interpreted as meta-theoretic dependent function space. Object theory lambdas are interpreted as meta-theory lambdas, and so on. And sorry, so all these lines here are each is one field in the model. In this record called model that I talked about before. Another application that we did, which is a much larger application, is the logical predicate interpretation from Bernardi and some Patterson's parametricity for dependent types. This is an interpretation from the syntax into the syntax itself. The type is interpreted as a logical predicate over that time, and term is interpreted as a proof that it satisfies the predicate, or it's as the parametricity proof for that term. And this might be used with some reflection to derive automatically derive parametricity theorems for our functions. And another application is that we are working on is pre-sheaf models and normalization by evaluation. So here, context is interpreted as a pre-sheaf over a given category, and then types are pre-sheafs, terms are sections, the technique of there's the technique of normalization by evaluation to show normalization of theories, and this from simple type theory this can be extended to dependent type theory, and currently the formalization of this is in progress. So there is some further work to be done. One point is that we used a very basic type theory, so we would like to extend this with universes and inductive types, and especially it would be, we would reach full internalization only if we interpreted or had the quotient inductive types in our theory. Also, we use some axioms in the meta theory, and like quotient inductive types, which also imply functional extensionality. This can be solved by using cubical type theory. And in fact, I was cheating a bit before because the meta-circular interpretation cannot be defined as easily as I told you, because if I truncate my syntax to be a set, then I can only eliminate into a set. So there are some ways around this that we did in our paper, but there's also the hope that there's the work of Nikolai Krauss on eliminating from propositional truncation, that this could be extended to eliminating from set truncations, and then we could have an elimination from elimination principle for the syntax to arbitrary types. And a nice future application of having an internal syntax for type theory would be template type theory, which might give some exciting applications. So given a model of type theory together with some new constants in that model, we would be able to interpret code that uses the new constant inside this model using some quotation, and then the code that we write could use all the conveniences of the host system, so implicit arguments and syntactic extensions and so on. And this would be a way to justify extensions of type theory, like guarded type theory or parametricity or homotopy type theory even. An interesting remark is that all of these extensions that we would like to justify are pre-sheaf models, except the last one, which is lives inside a pre-sheaf model. Yeah, and the code for all of our code is available on my website. Thank you very much.
Okay, now the pieces of my brain are even further scattered. So that was a very nice talk. Could you relate it to the previous talk? Because you talked about doing normalization by evaluation, which seems like a self-interpreter, so.
Yeah, so we didn't reach full internalization because we didn't define a universe in our type theory, in our object type theory. So we are not at the level of full self-interpretation. But if we added a universe, we would need an extra universe to self-interpret. So we need always one more universe to interpret a type theory with one less universes. Yeah. So here we need, if we had first universe, we would need in Agda, when we do all this internalization, we would need the second universe to be able to write down our internalization, even to write it down, and not to mention normalization.
Right. Okay, yes, that's very helpful to understand that you're working in a bigger type theory. That explains a lot. Also, you mentioned the work of Bernardi and others on doing parametricity, and I just want to say I really like that approach. It's a very syntactic approach, and it seems to work much better than the semantic approaches that are often used for parametricity. So I'll advertise my own work. I have a paper called the Girard-Reynolds isomorphism, which again takes the syntactic approach. And just, this is an audience filled of semanticists. I want to tell you, sometimes the semantics works really well, and I think that paper is a great example.
Thank you.